Hey everybody, it's Ben. Today we're going to talk about sequences. Now in math, a sequence is just a list of numbers that follows a pattern or a rule. So for example, I could have a sequence like this: 2, 5, 8, 11, 14, 17, 20, 23. Take a look at that. Think about what the rule for that might be. Or here's another sequence. I could have 3, 6, 12, 24, 48, 96, 192. Think about that rule also. For the first rule, you probably got it. It's just saying that each time I'm adding 3, plus 3, plus 3, every single time, all the way down. I always can find the next term just by adding 3 to the previous term. In fact, I could write that rule as a sentence. Add 3 each time to get the next number. We have a name for this kind of sequence where you add the same thing every time. We call it an arithmetic sequence. And the definition of an arithmetic sequence is just a sequence formed by adding the same number. We call that number that we're adding the common difference every single time. The second rule, you probably also could pick up on what the pattern was. In this case, I just multiplied by 2 every time, times 2, all the way down the line. We call this kind of sequence a geometric sequence. And a geometric sequence, just like you might have guessed, it's formed by multiplying the same number each time. And that number that we're multiplying, we call that a common ratio. By the way, you might be asking yourself, why does any of this matter? When will I ever need to use a list of numbers that follows a rule? Who needs lists anyway? Well, let's look at a few examples where this kind of thing might appear. Here I have a table with 6 chairs around it. And let's say we want to fit more people, so we want to add a second table. It's not going to double the number of people I can fit, though, because of the way those chairs on the end are going to have to move around. So if I put a second table into the mix, now I've got 10 chairs. I just added 4 chairs to my original 6. If I add a third table, I'm going to add 4 chairs again, so now I'm going to have 14. So what we're looking at here is an arithmetic sequence where every single time I'm adding 4 chairs to the previous amount. Geometric sequences show up even more often in more situations. Population growth is a great example. Let's say you start with 2 rabbits and the population doubles every 30 days. So 30 days from now, you're going to have 4 rabbits. 30 days later, you're going to have 8 rabbits. It's going to double again to get 16 rabbits, and then it'll double even again to get 32 rabbits. That's a geometric sequence. Let's take a closer look at how we would notate the rule for one of these sequences using algebraic notation like you would expect to see. So let's look at the first sequence. We said that this was an arithmetic sequence, so again, that meant that we're adding 3 every time, like so. And there's one problem though. Right now, we have this list of numbers, and we don't really have a good way to talk about where the numbers are in the list. So imagine with me for a second. I live in New York. We've got these old school delis where you walk in, or you want to get smoked salmon and this and that. The first thing you see is one of these red machines that has a little tag dispenser. And you pull the tag, and it gives you a number. The number tells you what place you are in line compared to everybody else who's waiting around in the store to get their thing from the deli also. So we're going to give every one of these numbers a little tag. The 2 is first in line, so we'll say that that's the first number. The 5 is second, so that gets a tag that says 2, and so on and so forth. Everybody gets a tag, and it's just saying where they are in the line. We call these numbers, these tag numbers, we call them n. And then the notation that we use to describe the actual value of the numbers that are in that place in line is we say a sub n. So we call it a with a subscript n. And this value a is the 2, the 5, the 8, and so on. Now, 1, 2, 3, 4, 5, 6, 7, 8, those are the values of the numbers in this list. But when we're writing an equation, we often refer generally to a sub n. So just understand that n can be any of these numbers that I'm looking for at a particular time. And I can also refer to the number before n as n minus 1. So I have a way of talking about the number that I'm looking for, and I also have a way of talking about the number that came right before it. The first kind of rule that we are going to write is a recursive rule. Now, a recursive rule is simply a rule that tells you how to get the next term in the sequence based on the previous term in the sequence. So for this particular arithmetic sequence that we're looking at, first thing we'd have to say is that a sub 1 equals 2. And then the next thing we would say is that in order to get a sub n, you have to take the previous term, which is a sub n minus 1, and add 3 to it. So this recursive rule is actually really similar to the sentence that we wrote originally to describe this pattern. In general, if I want to make a recursive rule for any arithmetic sequence, I need one other bit of notation, which is this common difference. In this case, we're adding 3 every time. We're going to call that number, whatever it is, d. So the general arithmetic sequence is always going to tell you the value of a sub 1, and then it's going to say, well, to get the next term, you take the previous term, a sub n minus 1, and you add d to it. The thing about a recursive rule is that it's kind of not that useful, because if you wanted to find the 20th term or the 50th term or anything like that, you would have no choice with your recursive rule but to count through every single number on the list before the one that you're trying to find. So we also want to find what we call an explicit rule for the numbers in the arithmetic sequence. An explicit rule is a rule that allows you to calculate any value you want from the sequence without having to calculate all the values that came before. So I really want a formula like this if I need to figure out the 50th term or the 61st term or the 79th term, because I wouldn't want to have to list out every single value in my sequence. Now, it's important that when I do this, I have kind of a pattern in mind. So in order to figure out that pattern, let's just use the 8th term here as an example. We're going to make n equal to 8. And let's count how many times I add 3 in order to get from the first term to the 8th term. So I already added 3 once to get to the second term and again to get to the third term. And then I added it a third time, a fourth time, fifth, sixth. I added 3 a total of 7 times to get to the 8th term. So I could write something like a sub 8 equals 2 plus 3 plus 3 plus 3, etc. 7 times. I could also kind of condense that and say that this is 3 times 7, and more generally I can observe that 7 is n minus 1 since we were saying that n was equal to 8. So that gives me a formula that looks like this. A sub n equals 2 plus 3 times n minus 1. And a general formula for an arithmetic sequence would then look like a sub n equals a sub 1, the first term, plus d, the common difference, times n minus 1. Let's try to do the same thing now for that geometric sequence that we were looking at earlier. So remember that in this case, the rule was that we multiplied by 2 every time. And just like before, we want to give every number in this sequence a value of n that represents its place in line. And then we're going to call the numbers themselves a sub n just like before. So we've got n, we could have n minus 1. All of the same labeling that we used for the arithmetic sequence works for this geometric sequence as well. Let's find a recursive rule. This is going to be very similar to that sentence that we wrote that said that we multiply the previous term by 2 in order to get the next term. So if a sub 1 equals 3, then the nth term is going to equal the n minus 1th term, the previous term, times 2. We can also write a general recursive rule for any geometric sequence. We would have to recognize that this times 2, we're going to refer to it as r for the common ratio. And once again, we would have to say that a sub 1 equals something, and then a sub n is going to be the previous term times r, the common ratio. Just like we did for the arithmetic sequence, we would like to find an explicit rule for our geometric sequence as well. We can find kind of a similar pattern that we found in the last one in this one. So let's make n the 7th term here and figure out what the pattern is. So I multiply by 2 once to get to the second term. I do it again to get to the third, again, a total of 6 times to get to the 7th term. So in this case, I'm multiplying by 2 n minus 1 times, and repeated multiplication turns into an exponent. So this could be a sub n is equal to 3, the first term, times 2 to the power of n minus 1. And this gives us a general rule for geometric sequences that says a sub n is equal to a sub 1 times r to the power of n minus 1. There were a few important formulas here, so let me just give you a slide where you can see them all in one place. The arithmetic sequence has a recursive formula and an explicit formula, and then the geometric sequence has the same. These are going to be really useful to you as you explore sequences more and you try to apply them to different problems. Maybe I'll make another video later where we do some examples, but I hope this helped you understand the concepts behind how sequences work, specifically arithmetic and geometric sequences, and how we notate the rules behind them. Thanks again, and I'll see you next time.